Hi, Ned Leckie with Leckie Engineering. This is going to be a brief demonstration looking at a Gocator snapshot camera for 3D hole recognition, used in conjunction with the UR5E and the LEonard software to kind of be able to build a unified and complete application. Okay, so start by just showing what hardware we have here and the different software components we'll be demonstrating. You'll notice that I've got a couple of security cameras that are running up on the screen. This kind of shows the Gocator mounted onto the end of the UR. I've got an Allen wrench taped onto this. That's what we're going to be inserting in the holes if we do all of this properly. Okay. If I take this video feed here and I make this a little bit smaller, I can bring over this web browser. This interface is actually the interface to the Gocator. So this will allow us to watch what the Gocator is doing kind of in real time, how it's making its measurements, what kind of measurements it's coming up with. It'll also be useful from time to time to take a look at OLIS Connect. This is teleoperation software. Again, it gets live feeds, in this case from a Bosler camera that's mounted up onto the Gocator, as well as a webcam that's here. And this is a very nice interface that allows you to actually real-time control the robot if you want. Helps for looking around and things like that. We might need it, we might not, but I always like to have it around when I'm doing demos or doing anything with the actual robot. We need some sort of a master of ceremonies here to command the robot, tell the Gocator when to do its thing, get CAD data from a file, which tells us where all the holes are, ostensibly, and then, do the alignment and make everything happen. And for that, I'm using the Leckie Engineering LEonard product, which we'll kind of fire up here. It makes these kinds of demos and deployments a much more straightforward kind of operation. You'll kind of get the sense of that. Okay, so with LEonard running here, the user interface here has very, very large buttons. I'm running the tablet version of this, so this is actually optimized for a 10-inch tablet, kind of more like a robot teach pendant. Makes it really easy to operate. There's also a version that runs on a desktop if that's your particular environment. Okay. First thing we'll do is, basically I'm going to walk you through a sequence of operations here. So the first thing we're going to do is we're going to run an origin program. I can kind of put this up large on the screen. I've got pre-programmed in here the offset from Gocator 0 to the tip of my Allen wrench. I am specifying in here the diameter of this cylindrical surface. I happen to know it's 32 inches or 762 millimeters. I'm setting up speeds and accelerations to be kind of what I want here, so I'm doing that. I'm selecting that I've got the Gocator mounted onto the robot. And specifying my part geometry. So LEonard knows how to run on flat, cylindrical, and spherical surfaces. And so we're going to make use of that capability so that we don't have to do any math in order to figure out how to hop around on the cylindrical surface. We can go ahead and just run this. If we go ahead and start this program, it's just going to set all of those points. It's going to go ahead and move to the origin. I think we're probably already there. It's going to trigger the Gocator just for fun. There's really nothing in particular that's worthwhile looking at there. But if we pull this up, we can see that the Gocator has been triggered. If I take a look at the countersunk hole tool or at the surface hole tool, it's looking down at this clamp that's at what I've defined as the 0 point on the cylinder. Okay, so that's kind of step one. Next thing we would do is we would say, okay, let's go ahead and try to figure out if our probe alignment makes sense. Okay, so here's a LEonard recipe to do that. It's going to move to a hole. I know there's a hole approximately out here at 9 inches, 1 inches. It's kind of this hole that's out in the part. I'm going to move out there. I'm going to fire the Gocator and adjust. And an adjust 3 is a 5-axis adjust. It's a XYZ and both rotation angles. And I'm going to trigger and adjust, and I'm going to do that a number of times. And then I'm going to move offset to the probe and see if I'm really aligned with the hole. Okay, so that's sort of what this script is going to do. And if I go ahead and start this, and then if we're clever here and we bring you back the Gocator, which I can kind of do like this, you'll see that we've moved out there, and now we're starting to do, these inspection routines. And I'm going to take a look at the countersunk hole tool that the Gocator is set up with, and you'll see that it's finding that hole, and it's been doing its alignment operation. And now we have moved down to kind of close to the hole, and what's happening is, we've got a pause in this LEonard recipe where it says, okay, hit enter to align to top surface. So if we hit enter, what's going to happen is we're going to move 5 thousandths more down in the Y direction. Okay, we're moving incrementally relative to the part. So we'll go ahead and do that. We just move down. Now it says, do you want me to insert? Well, I'm going to, make sure that I like the alignment here. Yeah, that seems to be, right on the money. I'm going to adjust my tool a tiny little bit. The tool can be adjusted to the offset because the tool is held to the side of the Gocator with a little bit of Scotch tape. So we're going to hit enter to insert. Now we've just inserted. You can see that part went in. I'm going to go ahead and hit enter to extract. Now we just pulled back out. Okay. And so this, basically this particular script, and now it's going to move back to this origin. This is really just a way for me to validate that the offset that I have between the Gocator and the tip of the Allen wrench is correct. Okay. And the way I'm doing that, I actually have created a command. So these are all the different LEonard variables that are in here. I've actually created an offset command right here, offset to probe. So movel incr part is a recipe command. We're moving incrementally relative to the part. So since this is a cylinder, the first coordinate is X, that's a linear move. The second coordinate is Y in meters, but we're going to automatically rotate around the part, so we don't have to worry about that. In this case, there's no rotation, but there is a Z offset. So we've got a Z offset to the tip of the tool relative to the center point of the Gocator. So that's kind of how we've set up that so that you can execute this command at any time, and that's going to offset you from Gocator 0 to tool 0. Okay, just like that. Okay, let's keep on moving. Okay, the next recipe that I'm going to run. Okay, things will start moving faster now that we have all of our pieces put together. The next thing I'm going to run is a static repeatability test. So I'm going to move out to a hole. Okay, once again, I can show you this. I'm going to use the file name of this recipe as a file name. I'm going to move out near a hole, and then I'm going to do a loop 5 times. I'm going to just find the hole, and then write that data to a file. Okay, that's what that particular LEonard recipe is going to do. So let's go ahead and run that. Okay, we can pull our views up again. We're moving off to this test hole that we've kind of set up, and we are firing the Gocator and then writing the coordinates that we've gotten from the Gocator out to a data file. So we let that thing run. It's 5 times. You can see the measurements all taking place. At the end of the whole process, it's like the last line. The last line of the function is to move back to the origin. So there we are. We move back to the origin. Operation complete. If I come over into my data directory here, you'll notice that we have just created a file called 10 static repeatability. Okay, that was the point of this whole operation. And if I open up this file, it's just comma separated values. If I open this file up and we take a quick look at it, kind of, you know, I've got timestamps here. It's it's 1:35 in the afternoon here in San Antonio, and here are my XYZ values. And even though the Gocator spits things out in actually microns, millionths of a meter, is the data that you get back straight from the Gocator, we're converting that into inches. So if you look at the repeatability here, we're getting very, very nice repeatability, you know, down into the certainly sub thousandth of an inch kind of repeatability. We can also look at these angles. This is the angle in degrees of the hole as measured by the Gocator. Those look very, very stable as well. Okay. Next thing I might want to do if I was going to be you know, testing and validating this machine, next thing I might want to do is a very similar kind of test, except this time, each time in between doing the measurement, I want to move out of the position, move back into position and read. So this is sort of a combined accuracy and repeatability robot plus Gocator kind of test. Okay, so we'll go ahead and start running this one. And if we do that, you know, once again, we're kind of moving over to a hole. We're triggering the Gocator. We are writing the data, you know, to that file. Then we're moving back to the origin and moving back to this static position again. Okay. If I do sneak over and take a look at what's going on in LEonard, you'll notice all of these variables here. GC is the Gocator counterbore hole numbers that are coming back. So this is how we're getting the actual return values from the Gocator. That's the counterbore hole tool, countersunk hole tool. There's also a hole tool that we had to use because not all of these holes have countersinks on them. And so there's a hole tool that gets used as well for the holes that aren't countersunk. And then to measure the normality of those holes, we use a plane tool. Okay, so basically what's happening there is as the Gocator is running, at the end of each one of its operations, it is spitting out a whole bunch of name equals value statements that go back to LEonard. LEonard sees these come in and just adds these to its list of variables. So that's a very easy integration. This is you have seen 100% of the Gocator program, you know, for doing all of these measurements and for getting the data back into LEonard. It's kind of a very nice way of doing things. Okay, we're done running here. We can sneak back over. We've got a new file, 11 robot repeatability. If we go ahead and open this file up and sneak in here and take a look. Come on. Open up our column so we can see what's going on. So now the only difference is we have gone ahead and moved the robot and then moved it back into position. And you'll notice we're still getting repeatability that's down into that thousandth of an inch kind of range. Our X and Y angles, you know, are looking really, really good as well. I'm not saying that this is good enough to do a statistical or a GR&R on this system, just showing you that we've got the tools to be able to do that. If we wanted to run this, you know, 100,000 times, if we wanted to be able to jog the robot a random distance, I'll show you how to do that in a little while. You know, we'd be able to test all of that out too, you know, very, very easily, you know, in the LEonard environment. I'm going to take a break right here. My coffee cup is empty. So we're going to stop here. When I come back, we'll start doing some alignment. Okay, I'm back. Let's keep on, you know, let's keep building on. One thing I'll point out for anyone, if you're wondering about this, one of the things that's built into LEonard is a very full-featured tool description sort of capability, a table of tools, if you will. And if we were to go down and take a look at that Gocator 3210 tool, the way that tool is described is there's 6 numbers, which are your X, Y, Z, and orientation. So that describes the orientation of the tool with respect to the faceplate of the robot. But you've also got the mass of the tool, the center of gravity of the tool, and you even got some digital IOs that you can turn on and off if you're using the tool. So this gets very useful if you've got a grinder or some sort of part finishing sort of tool, and you want to be able to control those digital IO. Those are all married to this individual record of what the tool does. Okay, we've also got mount and home position. So if the tool needs to be swapped and you need to get the arm into a very specific configuration because of dress pack considerations, things like that, that's all built in as well, so that we know how to, the system knows how to get the tool into the right orientation for dismounting or remounting, whether it's a manual dismount or an automated dismount, with an automatic tool changer. All kinds of other setup parameters, floating around in here. All kinds of logging and the ability to see what's going on, that sort of thing is going on. I've already shown you that LEonard maintains its own list of variables. It also maintains a list of positions, so you can teach positions in either pose or joint coordinates, move to them, do offsets from them, all kinds of things like that. Okay, let's keep moving. Number 12. So number 12, XYZ alignment. So what we're going to do here, we're going to go ahead and do something very similar to what we did in the last test, except we're adding on. So I'm going to move to a place where I know there's a hole, so about 2 inches by 2 inches. There's a hole out there. But then what I'm going to do is generate 3 random numbers between plus and minus 1/4 of an inch, 6.4 millimeters, right, is 1/4 of an inch. So I'm going to generate 3 random numbers, plus and minus 1/4 of an inch, and then I'm going to incrementally move in X, Y, and Z, just so this will be a random, move out of position. Then we'll go ahead and trigger the Gocator, and then we're going to do an adjust 1. So the Gocator adjust 1 only looks at the XYZ offsets and then moves the robot in the right direction to drive them to 0. Okay, so we're going to do this 5 times. The random numbers will be different every time. Let's go ahead and run it. So we hit start. I'll bring these other screens back so you can kind of see what's going on. We'll take a look at our measure output for the countersunk. And so what you're seeing is we're moving out. We just randomly offset by up to 1/4 of an inch in any direction. We ran the Gocator once, and then we reran it a second time. So we say, are we indeed, aligning? And this is going to happen 5 times. You can kind of see what's happening on the Gocator screen behind the scenes. You can also see what's going on, in the in the live world of video. I think we're probably just about done here. One more. As we can tell, the variable that we're decrementing is a variable called count. So if we come over and we take a look at count, count is down to 1. When count gets down to 0, we're all done. So there we are, and we just knocked out and we're done. So I can take a look at this data file now. We'll open this guy up here, and we'll go ahead and pull out his columns. And then let's take a look at this XYZ offset that is right here, XYZ. And let's go ahead and try to get a sense of what that all looks like. What I can do is just pull that up in a line chart, and let's see what we got. What the heck kind of a chart is this, and what does this mean? Well, what you can see is all the odd numbered instances are bad and the even ones are good. So we start off, we're off by a certain amount in XYZ. That the units on that vertical axis are inches. So you can see we're kind of off by up to plus or minus 1/4 of an inch as expected on these. The first readings are way off. The second readings, you're pretty much right at 0. Off 0, off 0, off 0, so forth. So again, now I've got now I've got kind of the beginnings of a GR&R to kind of say, hey, how well does this system work, and am I really aligning with the part? Am I confident that I could actually go try to stick that little taped on Allen wrench into these holes and not just make a fool out of myself on video? Is that where we're going? Okay, next piece. Let's go ahead and look at our other kind of holes. Okay, I'll show you what this looks like. We'll fire this up. On another part of this test part, we've got holes that do not have countersinks. So we're kind of moving over there now. You're watching me do the reading right now. The countersunk hole tool doesn't work over here. If I look at the countersunk hole, it's got all these invalid outputs in it. It doesn't work. If it doesn't see a countersink, then that tool fails. So what we've got is a surface hole tool that does a great job of giving us an X, Y, Z. It knows where the top of the hole is. What it can't see is the angle of the hole. This 3D camera can't really see the sidewalls of that hole. We can take a look at that, if you want to have fun. We can kind of knock ourselves over into 3D mode on the Gocator, and we can see, hey, it's got the hole nailed. It knows exactly where that is. You can see what the Z range, this large kind of column here, that's the viewing area where I'm looking in my region of interest. And the top and bottom of that are the limits of the Gocator, point cloud measurement range, right? So this tool does a very, very good job of finding the hole and the surface, okay? But I had to add one more tool, which is a surface plane tool. And the surface plane tool looks at this same region of interest. I've defined a region of interest out here. If we take a look at that. I've defined a region of interest, this one, defined a region of interest that is 30 by 30 millimeters, centered right on the center of the field of view of the sensor, and then the full range in Z. So I've got a 30 millimeter acceptance range for where that hole will be located. I'm doing that same region of interest for this plane. So we're fitting a plane to a cylinder, which doesn't strictly work. But it fits the best possible plane that it can to that area. It ignores the pixels that are missing, the point cloud data that's missing from where the hole is. And so it actually works out just fine. It gives us a very stable reading. And if we go ahead out here, now that this particular reading is done, that was the 13 XYZ alignment with a through hole. Once again, if we were to take a look at this data, and we were to go ahead and expand out our columns so we can see what's going on. These initial columns are all the countersunk hole readings, which are all coming back invalid. The XYZ over here, these are the readings that are coming back from the through hole tool. And we could do the same thing here, for fun. We could go ahead and insert a chart here and take a look at a line chart on this. And once again, what we would see is, we've got offsets. Now, the offsets are, kind of moving in both directions here. We've got offsets on all the odd numbered runs, and then the even numbered ones we're getting down to, perfect alignment. So this just kind of shows that the countersunk hole operations using the one Gocator tool and the through hole operations using the other Gocator tool, function. Internally in the code, the align function will use preferentially the countersunk hole data if the data is not invalid. Otherwise, it falls back and uses the hole, through hole. Okay, next. What's our next activity that we want to take a look at? Let's take a look at normal, okay? We'll do some normal alignment. So you you kind of get the idea here. We may not go through every single one of these tests. We may kind of jump, to the end here. But if I wanted to test normal alignment, I can go ahead and I can write myself a LEonard recipe. Here I'm moving out to a hole, and what I'm going to do is generate random numbers that are plus or minus 0.175. 0.175 radians is 10 degrees. Okay, so I'm generating plus or minus 10 degree random numbers, and I'm using them in MoveL Inker tool. An incremental MoveL, so it's a linear move about the tool endpoint, and the tool endpoint for the Gocator is its 0, 0, 0 point. So we're rotating about that focal point on the surface of the cylinder, and that's the command that I chose to throw in there. Then we're going to go ahead and we're going to do an adjust to, which only adjusts for angle. So this is, another way of kind of doing some testing here, seeing if we really like, what we're seeing. So this is going to be 14, normal alignment sunk. We'll go ahead and run that for a bit. And what you'll see, I think we'll go straight on here for a little while. So what you'll see is we've moved to position, and then we're on an angle, and that's why you've got these gradients on the surface of the cylinder. We're moving out of position. So we moved to this hole. Now we just rocked up to 10 degrees off in both angles. We're way out of position. We measured it. Now we're going to drive our angles back based on what we got out of the Gocator and go ahead and shoot it again. Okay, we shoot it again. Now we should be better lined up, and the system's going to go ahead and repeat this, over and over again 5 times. Right? That's what's going to be happening there. If we, well, we'll go ahead and let it finish up. Where are we? We're down to count equals 2. And you can see here are all the numbers that are coming back from the Gocator. We're on a countersunk hole here, so these numbers are valid. And again, what's coming in, the angle numbers are coming in milli degrees. So the bevel is 99 degrees. The bevel radius is 935 microns. These are offsets in microns from the 0, 0, 0 point. So this is how far out of position we are. And now we're done. Okay. So that's file number 14. Let's go take a look at that. And if we spread these out, so now instead of our offsets being the things that are, good and then bad, it's these angles, the X angle and the Y angle, that we're interested in. So I can go ahead and insert a chart, and we'll have that be a nice little line chart that'll look like this. And so this looks very, very much like our offset chart. The difference is now we've got the X angle and the Y angle in degrees. Okay, so we start off being, out of position. We would expect the positions to be off by up to plus or minus 10 degrees because that's how far we're moving it off. Looks like that's about what we're getting. The even trials are bad. The even trials are good. The odd trials are bad. And so this shows us that we indeed are moving out of position, running the Gocator, blindly accepting what it told us and moving back, and then we're getting the right alignment at that point. Okay. So, from here, we could go through all of these sort of, individual steps that I took in validating that I liked the way this combination of hardware was working. Eventually you move to a both alignment recipe where you're going to move out to some hole that you're interested in. You're going to randomly move yourself off in XYZ. You're going to randomly rotate in 10 degrees, and then you're going to go ahead and do several adjustments, okay? And adjust 3 is a 5-axis adjustment. And what I wanted to do here was kind of do that twice, and then add another kind of probably superfluous XYZ adjustment at the end, just to kind of see how things, behaved. And it's very nice to be able to quickly, build these recipes, change your mind about how things are going to work, and then go ahead and give that a shot. So let's run this one. We'll probably from here jump to the very end, of all of this. But if I pull back up my Gocator window, so now what you're seeing is we're moving out of position in both XYZ and both of the thetas, both of the angles, okay? And then we're moving back into position on all 5 axes. We're running the Gocator again. We're doing another 5-axis touch-up. And then finally at the very, very end, we're going to do just an XYZ touch-up and go ahead and see what that data looks like. We'll let this go through a few cycles so that you can get a feel for that data. And then I think, what I've basically done is I've taken you through my whole testing process for me to be able to gain confidence that this combination of hardware and vision algorithms was solid enough that I would have a hope of actually being able to insert that Allen wrench into each one of these holes. Okay, and that's really the last piece in the demonstration that we need to do today. Okay. We're back. This has completed. If we just pop over and take a look inside LEonard, we'll see that the application has run on our run screen. Everybody's green. We're kind of done with all of this. Let's go see what the data file on 16 both alignment looks like. So we'll come fire this up. And if we go ahead and make the column headings so that we can read things. So let's go ahead and let's take a look at the XYZ offsets. I'll go ahead and drop just a test chart in so we can kind of get a sense of, what all of that looks like. Put this line chart in. So what we would expect here again is, number one, you're way off. We've moved off by an XYZ offset. The next reading, by the time you get to number 2, you should be pretty darn close. Number 3 should be right on, and the next one should be, also right on. So this particular graph represents our XYZ offsets. We can come over here to X angle and Y angle, and we could do the same thing. We could say, hey, let's go ahead and drop in a line chart on these. So here you are. So now, we actually are aligning all 5 of our variables. You'll notice again that now these are angles. We're off by up to 10 degrees, and then very quickly, coming into, less than 1/10 of a degree, and so forth. So 1, is bad, and then 5, and then 9, right, and then 13. So it's a 4 cycle or a 4-step cycle, and every 4th one is bad, and then the next 3, get better and better and better. So, at this point, I think you get the sense, it looks like LEonard knows how to talk to the Gocator and collect all of the data. It looks like it knows how to move to holes. It looks like it knows how to build data files so that we can actually evaluate the quality of the readings. After all, are we going to, go through 10,000 holes and there'll be 3 holes that it can't read? We want to be able to collect that data and be able to understand, which hole it has failed on, and why. So the last thing that we'll go into is this inspect and insert. So we'll kind of look at that. Okay. So inspect and insert. If I come over to the program tab and we look at it on the big screen, what we're going to do here is the thing that's different is I'm not going to type in the coordinates of all 53 holes on my test part. That's not going to work for me. So what I am going to do instead is I'm going to open up an input CAD file, which is called holedata.csv. And I'm going to set up some scaling on columns 2, 3, and 4, and that is scaling to take me from inches to meters, basically, right? To meters, because the robot internally works with meters. And so if you look at this whole data file, this is basically the CAD data that describes my test part. There are 53 holes in my test part. The way LEonard works is any lines that begin with the word skip are skipped when you're reading through things. There's an ID number that will get kind of attached to any readings that we make. So each hole has a unique ID number, and all the readings that we take will be labeled with that, ID number. So if something does go wrong, we'll be able to quickly figure out which hole it was. And then we've got an XYZ in inches. So that these are evenly spaced in inches and relatively evenly spaced in Y as well in inches. And again, this inch measurement is automatically being turned into a translation and appropriate, rotation. Okay, so that's really the big thing that is new in this final demonstration. We're getting the hole locations from a CAD file. It's just a CSV file, and our inspect loop will be basically what this loop up here is doing is basically reading a line in. If that line exists, it's going to go ahead and call jump to a label called inspect. Otherwise, it's going to close the file and move the robot home. And what our inspect routine is going to do is it's going to move to that CAD location, which is relatively close to where the hole is. It's going to go ahead and trigger the Gocator. It's going to do an align 3. I could have it prompt me to, if I want to test, kind of single step this and make sure that I like what I see. We're just going to go for it. I haven't seen any weird behavior here, so those are commented out. That's what the hash sign does. So we're going to do an adjust 3. Then we're going to do a couple of other. We're going to do a second adjust 3. Then we're going to do an adjust 1, and then we're going to do an insertion routine. And once again, I've got a prompt here. Do you really want me to insert? Yes, no. I've got that commented out. We're just going to go for it. We're going to go ahead and move offset to probe. Then we're going to move in 30 millimeters, a little over an inch. We're going to move in 30 millimeters, move back out 30 millimeters, move in again 30 millimeters, out 30 millimeters, and then move on to the next hole. Okay, so that's kind of what this final example is going to be all about. So let's just go ahead and hit start. I'll pull up the Gocator. So you don't need to be looking at the Gocator, but it can be interesting to kind of see this as it goes. So we've moved out to the first hole. We're doing our multi-step alignment right now. After the multi-step alignment is complete, we'll come on down here. We'll go ahead and insert and remove, and insert and remove. And now we're ready to go to the next hole. Now I'm going to move this a little bit. Wreck my whole video probably, right? So we do some alignment and we do some angle measurement, and once we're done, looks pretty good to me. Okay, so this really kind of concludes the demonstration. I'll just let this thing run. It is making a data file, that cooks along. It kind of keeps on going. If you notice the position of the end of that Allen wrench relative to the sticky notes that are underneath it, if we jar that thing and knock it out of position, it'll be very, very obvious, that has happened. What I can do is, while this is running, if I go down into keep here, this is the 52 file. If I go down here, I guess I've renumbered these, but if we take a look at inspect all. I guess this is pretty good. That's not the data file I want. This is interesting. This just takes the CAD file and plots the data out as a scatter plot. So that validates that my CAD file looks like my part, kind of like that. But if we take a look at, let's look at this guy. You can see the system is still running along, behind us here as we go. So this is what happens if you run this data file. The data that you get is kind of all like this. You got all these adjustments. As I get to the very end of the part, this is where I have 9 through holes. So those last 9 holes, that's where I start getting invalids out of my countersunk hole, but my other holes are hanging in there. And if you take a look at my offset graphs, so this is translation error on the countersunk tool. What you'll notice is the initial error is actually progressing. That's because when this data was run, I was telling the machine that I had a 1,000 millimeter diameter instead of a 32-inch diameter. And so what that means is that the initial rotation wasn't actually accurate. I was slowly getting farther and farther away from the part, because instead of 32 inches, I was thinking that it was 39. So I was slowly getting farther and farther away from the part, and that's why the gray line here, the Z offset, is getting worse and worse and worse as you move to these holes that are progressively farther and farther away from top dead center. So here I had the wrong diameter and just kind of let the thing run. Well, who cares? The first shot, it's off by more than you really would like it to be. But by the time you get into the second and third shots, you're right on. Okay, and so that happened here. What you're looking at is the last 9 holes don't do well on the countersunk hole tool, but the through hole tool does great on them. And this noisy stuff here, these are extra large holes that are out in the middle of the part here. Those are extra large holes, and my through hole tool was programmed to not allow things that were that big when I ran this data. So it was kind of rattling around in these big holes. He was very, very noisy, but I don't care, because at that point I was using the more reliable data from the countersunk hole tool. So this, shows, gee, I had the wrong diameter. I was in the wrong spot when I started, and I still stuck the wrench in the hole, every single time, right? Angles, the angles on this pre-computed data, similarly, very much the same. I see this progression in the X angle, and that's because, I had the wrong diameter dialed in here. So I see this progression in that, but I still see myself driving back, to 0 on these subsequent, goes. If we go back up to the data that we're running here, we'll take this 52 file. I will make a copy of it so that I can open it up without interfering with poor Leonard that's trying to append lines to this thing. If we go ahead and we take a look at this data and expand out our columns, then once again, we're looking at XYZ offsets, and just visually I can see that they are repeatedly going to 0. If I want to make sure that I really like the way that looks, I can go ahead and punch in my line chart, something like that guy. And so there we go. That's our XYZ offsets, okay, which are coming in. I'm not seeing progression in the initial Z offsets now, because now I actually have told the thing, hey, you're 32-inch diameter. I'm not running you pretending that you were 1,000 millimeters anymore. And if we went back and took a look at our angles, X and Y angle, and we took a look at those for this work in progress data. Once again, what we're seeing is we start with whatever is in the CAD data, and then we very quickly drive back to zero on both of those angles. Okay. One last file I can show you. This is a full data set again, but this is what happens if you move to the location of the CAD data. So you move to the location of the CAD data, but then you knock yourself off 1/4 of an inch and you knock yourself off 5 degrees. Okay. Now, I thought we were using 10 degrees. Why 5? Well, as you run all over this part, if you rotate 10 degrees that way, you can smack into the robot. You run out of room. And if you rotate 10 degrees on the far holes, you can wind up running out of robot in the other direction. So, I restricted that a little bit. But here, with this data, here's the countersunk tool. These are angle offsets, actually, that we're looking at. And this is where I'm moving to the CAD location and then randomly perturbing and then going from there. So the initial misalignments here are much more random. There's no systematic story that we can see in that. The only important thing is that at the end of the day, we've properly aligned and everything's looking good. Same thing happening here. We've got random misalignment to begin with. This is a 1/4 of an inch is sort of more or less the maximum here. And the same thing is happening. We're seeing that hole tool do weird stuff on really big holes. I don't care because I'm using the countersink tool on those. And then when I get down into the actual through holes, that hole tool, gives me exact performance, exactly what I want. Okay. Come back here just to close out. You notice that our tool is still hanging in the same location that it was in when we walked away, from the story here. We're continuing to do our alignment. We are then, going down and doing our insertion routine. Looks like we're right on the money here. I have to say, this is not an easy imaging application. This is kind of a nasty, rough surface 3D printed part. It's quite shiny, the plastic that's here. And in general, I would expect some significant imaging problems if I was using traditional 2D imaging techniques. I would certainly not be confident turning my lights on and off, and things like that while I was, if I was doing a 2D vision application here. Let's let it do some imaging with the lights off. Probably look pretty, right? So they were doing some imaging. You may have noticed there's a small red laser spot that you occasionally see. I've actually got a laser triangulation sensor on the back of the Gocator, and it's pointing down to just about almost these XYZ location of that. Really just using that for alignment, and it's not being accessed in the program at all, although it certainly could be. It's one of the things LEonard is very good at interfacing with all kinds of different devices. We've interfaced it with PLCs over SIPC. It does Modbus. It does Profi. We've talked to all kinds of different vision sensors. It talks to all of the I/O on the UR, so that gives you access to some analog I/O as well as a bunch of digital I/O. I've got a PLC hanging on the end of my table. I shoot Modbus commands to that all the time, to get that working. So I won't make you suffer and watch through, all of these different alignments. I do have some hyperlapse video somewhere on this channel that actually shows the whole thing going through. So if you're interested, you can take a look at that. But the purpose of this video is mostly to show you what the tools are and the LEonard technology for knitting all this stuff together and very easily making our kind of complete application and having that, operate here. Thank you so much for your attention. And you know, any questions or comments that you have, we're always very, very happy to get those. So thank you very much. Ned Leckie, Leckie Engineering. Have a great day.